Okay, let's get started. So first, a reminder about review session. And I'm remembering on a Wednesday. This is the second Wednesday I'm remembering. Go me. It's a terrible track record, but 2 wins. I'll take it. So review session every Wednesday right after class for, I want to say 2 hours, right? It is on Twitch, so go on to Twitch and get your review session on. Especially if you have any questions. I pop in every once in a while, lurk in review sessions just to see what's going on. When I have, it's usually just the TAs sitting there, not doing a whole lot. They have some content prepared, but then they open it up for questions for most of the time. The whole idea is that you should come with your questions because they don't know where you're stuck. They don't know what you need to hear. So they'll prepare a little bit to review the content from the previous week. But they'll mostly wait for your questions. So come there with questions, ask them questions, challenge them, make them think and make them work for it when you go there. And if you have questions about, the big topic right now is point of sale. If you have questions about point of sale, go in there and pick their brains about point of sale. Ask them questions about the homework. Say, man, I'm really struggling with LT5. I don't understand how to implement the state pattern or what's going on here. And they probably won't help you directly too much with the homework, but what they'll be able to do is show you more examples of the state pattern, more examples of object-oriented programming, and maybe clarify what the homework is asking you to do if that's your question. They'll be able to do that for you. So if you want more examples about, all kinds of things, please take advantage of that resource. And even if you miss it, if you can't make it live, they do post the videos on the YouTube channel. And watch the recap, watch the VODs of them. But take advantage of that resource. I see, just looking at the stats before lecture, point of sale isn't going as well as I want it to. The homework's never due. I always want things to be stellar. I would like everybody to be done with point of sale by now, because we're pretty deep into genetic algorithm in lecture. Like, if you're still working on point of sale, the class is leaving you behind a bit, which is most of the class. Still working on point of sale. But anyway, take advantage of that resource. If you're in that position, which most of the class is, and you're not taking advantage of all the resources, there's not a whole lot we can do for you. If most of the class is going to do what students do and just wait to the last minute, and then everybody's going to work on point of sale on Friday, I mean, it's what happens. It's whatever, but we're very limited in how we can help you when you do that. What's up, Dragos? What's up, Weird Alex? Cole, what's going on? Anybody have questions before we get into it, before we start talking about immutability? Everyone's going to come to review session with their questions. And by the way, I don't like seeing my TAs get off the hook so easy. When they're in review session and they're just sitting there and chat's almost dead, make them work. I want to see them working. I want to see them, I can't use any of those phrases during lecture, but I want to see them working hard. Put them to the test. Ask them questions that they might not know the answers to. I want to see them sweat a little bit, too. Make them work. Even if you don't have any questions, just go there with your really crazy complex questions and just see what they say, see what they do. Anybody have anything before we get into new content? Let's do it. Immutability. So we've been embracing immutability all throughout genetic algorithm, all throughout functional programming. Immutability is kind of the opposite of what we've been doing in OOP, the opposite of what we're doing with objects and classes and the state variables, the state pattern, things like that. It's saying no variables. Any value that you're storing can't change. That's what immutability is saying. We'll talk about it all lecture. Which comes along with lecture task 4 of genetic algorithm. In my opinion, I believe this is the hardest lecture task in genetic algorithm. So once you do get past this one, or if you're stuck on this one rather, jump ahead to 5 and 6, get those ones done, and then come back to this one. And once you get done with this one, it's downhill for the rest of the assignment, unless you're going for the application objectives. Application objective 1 is, of course, way harder than probably all the lecture tasks combined. And then AO2 of this one, I mean, I don't know the best way to word it, but don't even try AO2 unless you have a very solid grasp on all the content. AO2 is tough. By design, that's meant to be a challenge. But anyway, lecture task 4. The first part of this, adding the add rating method to the song class, this one isn't too hard. We just need that method to exist to be able to do the second part of this one where the true difficulty lies. Add rating, which you're going to add a rating to the song class. The song class is going to store all of the ratings of a song. So any user who's rated a song, the song should remember that and have a data structure storing all those ratings. But that data structure has to be immutable. So we need a way to be able to add to that data structure without changing it. How are we going to do that? Well, we're going to return a new instance of the song class with that change applied to it. So that's the key to immutability. Whenever we need to make a change to an immutable object, we're going to create a new object of that type with that change applied to it, and then return that new object. So we're creating a new object every time we need to make a change. And that's going to be our key pattern for immutable objects, is create new objects. We're going to create all kinds of objects. We're going to have lots of objects on the heap because we have to create a new object every time we want to make a change to an object. And then the next one, this is the bulk of I shouldn't say the bulk, but the most difficult part, in my opinion, of the lecture tasks of genetic algorithm, this read songs from file. So there's a file full of songs. It's a CSV file in this format. YouTube ID, artist, title, rating, energy rating. And the song class has state variables for all of these values. Of course, they're all vals, they can't change because song is an immutable class. And you need to read all the songs of this file one line at a time and return a data structure, a list of all of the songs containing all of the information in this list, or in this file. To do this, you'll be pulling out your ideas about immutability, data structures, and most of all, recursion. You'll have to use recursion over the lines of the file to get this one done. This one is a pretty difficult recursive method to write. So, like I said this a few times already, so this will probably be the last time I say it, except in office hours if you ask me questions. You should be writing lecture task 3 using recursion to kind of warm up to writing a recursive method. That should be the first recursive method you write is LT3. Even though you can cheese it, you can do it without using recursion, but you kind of need to get practice to write this one. This recursive method is a bit tougher, and then AO1 is a much tougher recursive method to write. So you should be getting your practice in LT3 to be able to write this type of recursive method, which takes in a lot of the tricks that you've seen throughout the past few lectures and throws them into one pretty tough method. Namely, if you're struggling with this, if you're on this one already and you're struggling with it, try writing a helper method that takes more parameters than you need and then defer to that helper method to be able to write your code. That's going to be very helpful in this one, in this method. And even though you're supposed to return a list, maybe use a map at some point to help you out. So those are my hints if you're on that one already. I think most of the class is not on this question yet, but if you are, those are my hints for you. There is no testing in Autolab. This is strictly a logistical constraint. Since we have to do file I/O, and you can have different files, and you should have different files for testing, that just gets really messy in Autolab to be able to test your tests and find your test files because the directory structure gets all changed around. So there is no testing, but please, my goodness, that does not mean you should not be testing. If you don't have tests and you come to office hours with no tests, without even a main method that you're calling to be able to test these things, your only question in office hours better be, how do I write tests for this thing? And my answer, I'll give you a little heads up on this. If you ask me how to test this thing, don't test on the entire file. There's a file of songs, song ratings in the repo. Don't test on that entire file. Take like 5 to 10 lines out of that file, create a separate file, and then use that as a testing file. Then it's a lot easier to compute what should be returned, and at least have one test case where the file that you use rates the same song multiple times. That's where a bigger challenge comes in with this. If each song is rated once, this isn't too bad. Once you have songs that are rated multiple times in the file, and you have to update those songs, that gets a little trickier. All right, I think I talked about that enough. Let's talk about what immutability is. Immutability, immutable objects specifically is what the context we'll talk about this in. Immutable objects are objects where the values in their state variables cannot change. So no vars in any of the state variables. Vals only, or if it's in the constructor, if you don't use val or var, that's fine too. Just no vars anywhere in the code, which of course is what we're embracing with genetic algorithm. No vars allowed. Anywhere, immutable objects is when no vars in those state variables, no variables, strictly state values, which isn't really state anymore since it can't change. So these objects still go on the heap, just like every object in Scala. Shouldn't say every because any object that extends any ref, I'll say. But we're not worried about the pass by reference feature that we had before. When we talked about OOP and we talked about the heap, we were worried about things on the heap changing state because we were passing references to these objects. And then the state could change, and we'd see that change in state somewhere else in our code. Even if we called a method that returned unit, that method could still make a change on the heap, and we'd see that change outside of that method after that stack frame was done and destroyed and off the stack. With immutable objects, we still pass those objects by reference. We pass references around our code, except we're no longer worried about the state changing from under us because the state can't change. There are no variables in the state, so we're not worried about that state changing when we call a method and give it a reference to our object. So what if we do need to change the state? Or what if that method we call needs to change state? Well, it's going to have to create a new object with that new state applied. So it's going to create a brand new object. That leaves our object that's on the heap completely unchanged. But they'll create another object on the heap with the change, and then they'll use a copy of that. That method will use that copy and then do whatever it needs to do with that. Sometimes it'll return that object, and then we can decide if we want the original object or the altered object in our calling code. But the state can't change from underneath us, so we're going to create a copy of the object with the changes if we ever want to make a change to an immutable object. So here's an example of an immutable object. As simple of an example as I could think of, it just has an int, and you can increment and decrement that int. That's all this class does. Not super interesting, but it shows us an example of an immutable object. So this counter int can't change. I'm not using val or var right here. So it's by default val, and as an extra bonus, it can't even be accessed from outside of the class. So we can't even read this variable from outside of the class. We don't know what counter is from outside of class. So if we do want to see what counter is, we're going to have to call this print counter method. We can access counter from inside the class. So this method is just going to print out the current value of counter. But our code can never know what that value is because it can't read it from outside of this class. So if we want to make any change to counter, one, we just can't do it. But if we want to simulate a change to counter, we're going to create a new object of this type with the change applied. So if we want to increment the counter by 1, we're going to create a new immutable counter object. It's a new object on the heap. And we're going to give it whatever the current value of counter is, plus 1. If we want to decrement it, same thing, we'll create a new object with whatever value we currently have in counter, minus 1. So we're creating a new object with the change that we want applied to it. So if we create a new immutable counter where the counter is 20, and we call decrease, decrease is going to return a new immutable counter where counter is equal to 19. So that's a way that we can simulate decrementing this counter, even though the object's counter variable cannot change. Whenever we want to make a change, we're going to call one of those methods, and we have to use the return value of that method call, which will be a reference to a new object, if we want to see that change. So when we call increase or decrease, we have to use that return value. There's no state change, so if we just call counter.decrease on its own line, we're not going to see any of the changes because the object that we have a reference to has not changed. So we have to use the return values. These immutable counters that are returned, which are the new counters with the change applied, we have to use references to those returned objects. So let's take a look at the rest of this code. Like, we have methods to increment and decrement the counter. But what if we want code that's going to increment the counter 10 times? We're very limited in what we can do because of this class. We can't even read the value of counter, so we can't just say counter plus 10. Can't do anything like that. We have to call increase and or decrease. That's all we can do, the way this is set up. And I did that to require some recursion because I want more examples of recursion in our lives. So we would normally just use a loop. We would loop 10 times and call increase 10 times, but that's going to require a var. We're going to have a variable because each time we call increase, we have to reassign the returned object to our variable. So loops are out of the question. We're not going to be able to get this done using a loop. We could hard code it. If 10 is the only thing we want, we could say counter.increase 10 times, and then reassign that to a value. But what happens when we decide, oh, we actually want 30 times now? That's going to be very rigid, very inflexible. So we're going to pull in our friend recursion and do this recursively without using any variables. We're going to embrace immutability and have a recursive method to be able to do that. So I'm going to write this update counter method, which takes an int n, which will be the number of times I either want to increase or decrease the counter, depending on whether it's positive or negative, and the counter that I want to change. And I'm going to return a new counter with the change applied. So what I want from this is that if I create an immutable counter where counter is 10, and I want to increase the count by 20, I'm going to call update counter, increase it by 20, give it a reference to this counter, and what that will return is a reference to a new counter that I'm going to store in this variable, which will store the new count that I'm interested in, which should be 30 if I did my math right here. So this should be incremented 20 times from 10. This should print out 10 still because its state cannot change, but this one should print 30. This is a new immutable counter with that change applied that I'm interested in. So to write this method, we're going to pull out our ingredients for successful recursion. We're going to assume that our method is correct, build our logic around recursive calls around that assumption, write a simple base case, and make sure all of our recursive calls get closer to that base case. If we have those 4 ingredients, we should be good to go, and then the magic of recursion kicks in, and our algorithm just is correct. So update counter, I'm going to start with my base case. If n equals 0, if you're saying increment this 0 times, I'm just going to return the counter that you gave me. I'm just going to return a reference to that same counter. If you're asking me to increment this thing 0 times, there's no work to do. It's already done. So trivial input-output behavior. Your base case should always be this simple. As simple as it can possibly be. Increment this 0 times, that's as simple as I can get. I'm just going to return the counter, done. It's similar to sort this list of one element. I'm just going to return the list. It's already sorted. What are you asking me to do? It's already sorted. It's one element. You want me to increment something 0 times? It's already done. Here you go. Here, just have it back. Base case, easy. The recursive calls are going to make some decisions. Here I actually have 2 recursive cases. If n is not 0, I want to know whether it's positive or negative. If it's negative, I'm going to call decrease. If it's positive, I'm going to call increase. Now I'm going to assume that my recursive calls are correct. So if I'm asked to increment, if n is positive and I'm incrementing, I'm going to make a recursive call to update counter. I'm going to call increase one time, and I'm going to ask the recursive call to increment n minus 1 times. So for example, when n is 20, I'm going to call update counter 19 and increment the counter by 1. So call increase once. So the 20 effectively means call increase 20 times. I'm going to call it one time and make a recursive call that says, okay, with this new counter that was returned, you still have to call increase 19 more times. And then that's going to make a recursive call that says, okay, I'm going to call increase once. Recursive call, you got to call increase 18 more times. That's going to call increase once. Make a recursive call, you have to call increase 17 more times. And so on until we get down to 0. Once n equals 0, return the counter. And then that counter should have the final answer, which is just going to be returned up all the way up the recursion. So if my recursive call is correct, then to make a recursive call that's getting closer to the base case, our final ingredient, I'm going to call increase once and make a recursive call that's one step closer to the base case and says, hey, call increase n minus 1 more times. So our 4 ingredients are met, and then this recursive algorithm should just work. And whether n is negative or positive, if it's negative, we're incrementing n. If it's positive, we're decrementing n. So we're always getting closer to that base case of 0. Every call is getting closer to the base case. Our logic built around the assumption that our recursive calls is solid. And our base case is trivial input-output behavior. And we're assuming that this is going to be correct. Our 4 ingredients are all met. So we got some solid recursion here. We're going to get the right answers, the answers that we're expecting. Any questions on this example? We were talking about immutability, but we also got another example of recursion in there. Any questions about immutability or recursion that you'd like to see about this example? If not, I'm moving on. So immutability is not a new concept. It's not a new topic. You've been dealing with this a lot. I just haven't called it immutability until today. And guess what? Strings are immutable. Strings you've been using all semester. You may have noticed, if you're really observant, that I never used strings when we were talking about heap. When we were introducing heap examples, I said strings go on the heap, but I never gave an example of that. And that's for good reasons, because they're immutable, and they behave a little differently than what we wanted to talk about when we first introduced references, pass by reference, heap, references on the stack, things like that. Strings behave a bit different. So let's talk about how strings behave due to the fact that they're immutable. We're going to look at this example here. I'm going to break this down line by line and show you the stack and heap. But let's absorb the code just for a second. We have some strings that we're creating. We're going to call some methods that take strings. This one returns unit, take a string and return string. And we're going to put some things to the screen. The code itself, you should be able to follow since way earlier in the semester. But I want to show you what's happening on the heap and why it matters that strings are immutable, which is something you've had to care about all semester up until this point. But I want to explain why you had to care. So we're going to start at the main method. Course string goes on the heap. That's an object on the heap, and we get a reference to that object. I'm just going to use @1. Again, the numbers are arbitrary. I just pick random numbers. For this example, I felt like using 1, 2, 3, 4, and 5. We'll see eventually. And then I'm going to call nerf with a reference to that course. So I'm going to create a frame for this method call. The parameter input is going to be assigned the value of the argument, which is a reference to this object on the heap. And then I'm going to call this method, input.replace 6 with 5. This method is going to work with our immutable string. Input is a reference to an immutable string, meaning this value will never change. This value will always be CSE 116 in the heap for this object. So when we call input.replace, what's happening is we're getting a brand new object on the heap with the change applied. Now, whenever you call one of these methods on a string, whenever you change a string, you inevitably ran into a bug where you just didn't see the change. The change didn't seem to take effect. And the bug is when you don't reassign the output of that method to your string variable. You didn't do like s equals s dot replace whatever. If you don't do that, you're never going to see your change. Because the string is immutable, so when you call this method, you're creating another object on the heap with the change applied. And then in this case, since we're not returning anything, we have return type unit, and we don't reassign anything, guess what happens to that CSE 115 string? Nothing. We don't get to see that change. Our code effectively can't ever access that string. And in fact, it'd actually get garbage collected in this case. It's something we don't really talk about in this course, but this will get garbage collected because we can no longer access this object. So we return unit. We move on with our program. And nowhere from our stack variables can we ever access this object. We never reassigned it to a variable, one, because we don't have variables, but we could have assigned it to a value and then had access to that string, but we never did that. We never even returned anything from this method. So this is just hanging out there, waiting to be garbage collected, because we can never access that string. So this is why we always had to reassign. We would have to say, val x equals nerf, of course, and then have this return a string. Then we could actually have access to that change. We don't have access to that change because it's a different object on the heap, and we never assigned it to anything on the stack. So let's move on to a method that does do this the way we want it to. Amplify. It's going to be a new frame on the stack. It's going to get a reference to that same string at 1, which contains the value CSE 116, which again will never change. But when we get to the last slide, this will still say CSE 116. It cannot change. Strings are immutable. We're going to create a new string, replacing 116 with 250. This returns, or replace method returns a new string with the change applied. It does not modify the input, the original string. It does not modify this string. Creates a new string with the change applied and returns it. This method actually does have a return type, so it's actually going to return that string. So the stack frame is going to be destroyed. Return this reference at 3, which is this object here. And then we're actually going to store that in a value on the stack as well. So we're going to create a value named data structures and assign it the return value of the amplify method, whatever that stack frame returned, which is this object right here. We actually have access to that on the stack now. So the first method call, that's the way we introduce bugs. That's going to be broken code that doesn't work. The second method call, the amplify method call, that's the way we want to do things. That way we can actually see the changes that we made, well, the changes that we made to an immutable object, because we're storing a reference to the new object that was returned with those changes applied. And again, this never changed. Of course, this will always refer to an object with the string CSE 116. Same thing here. Course plus is great. Creates a new string. The concatenation method will create a new string with the change applied. So we get a new object with that concatenation on the heap, but guess what? We never assigned it to anything. So we don't get to use that string. That string that was created, we move on. We look at the we look at the stack and we see we don't have a reference to @4 anywhere. We created this new object, and we just walked away from it. We said, create it, told Scala to do all this stuff, allocate space on the heap, make these changes, concatenate these strings, and we just walked away from it. We said, you know what? I don't actually care about that value. It's kind of wasteful, because we didn't reassign it to anything. We didn't assign this to anything on the stack. We didn't say val whatever equals, so we can never access this in our code. Once we go past that line, this object might as well not exist. The way we need to do things is the next line, assign it to something. Val course string, now we're creating a value that can store a reference to a string, and we're going to assign that the concatenation of these two strings. Get that object on the heap, store a reference to it on the stack, and now we actually can access that. Then we can print out those three values, but we can never access @2 or @4. And technically, if you're wondering, there would be a lot more strings on the heap. The string literal 6, 5, 115, or 116, 250, space is great, and space is fun. All of those strings would also be on the heap as separate strings. I didn't want to clutter up the slide too much, but all of those strings would also be on the heap because those strings have to be created before we can call methods on them. Every string literal is going to go on that heap. They're candidates for garbage collection as soon as we move on from them because we can't ever access them again, but they would be on the heap. Strings are immutable. So when you had that, you probably ran into it in 115. In any language I've used, at least, strings are immutable. Oh, can I say that? Might be too strong of a statement. In C, I guess they're not. But in a lot of high-level languages, strings are immutable. So you probably ran into this right from 115. Early in 115, you had some strings. Maybe you were concatenating. Maybe you were doing a replace. Maybe you were just modifying the string in any way, and you didn't reassign it to your variable. You're going to be panicking and being like, why is this not doing anything? It's because you have to reassign the reference to the new string that was created back to your variable, or create a new variable to store that change, that object with the change, because strings are immutable. No questions at all? Chat's pretty quiet too. It is that part of the semester though. I know I've been wearing down too. It's brutal. I always say that the spring semester is so much better because this week right now would be spring break. We'd have a break right now. But in the fall, we don't get any break right in the middle. We all just have to plug through, chug through this thing. So I feel you on that. I'm wearing down too, but it's part of being in a fall semester, unfortunately. Plus, you have the project due Friday. I'm sure that's part of it, too. It do be like that sometimes. I'm not allowed to say that phrase. All right, let's move on. I'm dreading LO3. LO3 isn't. I've said this before, but I don't think LO3 is worse than LO2. I always say that it'll be easier just because you're more experienced by the time you get into LO3 stuff. At the same time, I guess it might be a little harder too, just because you're more worn down by the semester. And it's, you're probably in the middle still of midterms and other classes. So it's just a rough part of the semester. But you shouldn't dread LO3 for its pure difficulty. It should feel easier than LO2, especially the lecture tasks. Lecture tasks 5 and 6 on LO2 on point of sale they're tough. There's no getting around that. LT4 on genetic algorithm is tough. But the rest of the objectives, they're manageable. I think they're very manageable. You can cruise through them if you're keeping up with lectures and stuff. You can get them without too much difficulty. And part of that is I know functional programming is a difficult topic, so I try to not write, ridiculous. It's easy for a question to get out of hand, because I'll be like, yeah, it's just recursion. Throw the 4 ingredients at it and it works. But I realize how hard that gets when you're first doing recursion for the first time. So I try to keep them very manageable. LT4 is the place where I'm, challenging you a decent amount. I still don't think it's too ridiculous, but it will force you to understand the things I've talked about recursion. So that one's pretty tough, but you'll be able to get through it. You'll be able to manage, I believe, especially with the structure of the course. And then LO4 is not hard. I try to ease off with LO4 because I know finals in other classes are kicking your ass at that point. I want to ease up a little bit. I try to do that in all my courses, or most of them anyway. My last part of the course eases up a little. I just try to dominate your time in the middle of the semester, and then after that, back off. All right, no questions? Lists are immutable. Been using lists all semester. Lists are immutable. We'll see the same thing that we saw with strings. Whenever you make a change to a list, append, prepend, remove an element, call it drop or something, you always have to reassign that to your variable, or else you won't see the change. It doesn't actually modify your lists, because lists are immutable. You can't modify the elements of a list. Once you have a list, that's what the list is, forever, for its entire life. You can't change a list in Scala. There is a mutable list option in Scala. Of course, you can't use it for genetic algorithm, because it would bypass the entire point of the assignment. But by default, the regular list, immutable, can't change it. All you can do is call methods that create new lists, return the new list, and then you can reassign that to a variable, or assign it to a new value to be able to kind of simulate changes with lists. This is one of my favorite examples. We're going to use recursion twice in this method. Both of these methods are recursive. So I'm trying to hammer down recursion while continuing our conversation about immutability. So if you have questions on either of them, list buffers aren't allowed either. So if you have questions on either of these topics, here's the example for you. This first n primes is going to return the first n primes. So for first n primes of 3, I should be returning a list containing 2, 3, and 5. That's what this method is going to do, this first n primes. So I wrote that method without using any vars to embrace immutability, and we're going to step through this program and talk about how we get this done while focusing on the immutability of the list. All right, so we'll skip through the regular stuff. First n frames of 3, we get that call right here. Get that frame on the stack. 3, we're going to hit the else. The first thing that does is make a call, first n primes, a recursive call of n minus 1. That's going to make a recursive call of n minus 1, and now we're at one of our base cases. Our base cases are n less than 1. If you're asking me for the first 0 primes, I'm going to give you an empty list. If you're asking for a negative number, I'm going to give you an empty list. If you're asking for the first -5 primes, I'm just giving you an empty list because what you doing? Why are you even calling my method like that? I'm just going to give you an empty list because I don't know what else to return there. Should I give you the first n primes but negate them all? I don't know. I'm just giving you an empty list. Stop calling my method with negative numbers. If n is 1, this is my true base case. If n is 1, I'm going to give you the first prime. This is how I'm defining what the first prime is, because we could debate that. Is 1 a prime? Is the first prime 2? Is 2 the 0th prime? And if somebody's asking for the first prime, should you give them 3? I'm going to answer all those questions right here and say, if you ask for the first 1 primes, I'm going to give you just the prime 2. I'm going to say that's the first prime. 1 is not a prime. First prime is 2. So that's my trivial input-output behavior. Ask me for the first 1 prime or the first 0 primes. Give me an empty list or the list containing the value 2. You'll notice, just like one of our examples last time, the base case is the only time where I'm actually creating a new list. I'm never creating a new, I am never creating a new list beyond that. I'm just modifying an existing list, but as we know now, lists are immutable, so I'm actually taking that existing list, creating a new list based on that one with the change applied that I want to make, which is going to be prepending a value to it. So in the base case, I'm creating a new list with the value 2. That's going to be returned up to this stack frame where n is 2, and this is going to return with the list containing only 2. I'm going to create max prime, which is going to take that list of primes and find the largest value in there. So, and let me back up a little bit. So I made my recursive call. I said if my goal is to find the first n primes, I'm going to make a recursive call that gets closer to my base case and just assume that it gives me the right answer. So if I make a recursive call for n minus 1, I'm going to say my task is to find the first n primes. I'm going to make a recursive call and say give me the first n minus 1 primes, which gets me closer to the base case. And I'm going to assume that that's correct. So my n minus 1 primes is going to be the first n minus 1 primes. Assume that's correct and build my logic around that. And then the rest of my logic is finding the greatest prime. What's the largest prime that I've found? And my task is now to find the next one. So the greatest prime I found is just 2. And my task is to find the next prime that's strictly greater than 2. As long as my logic there is sound, then I'm going to return a list that finds the next prime, prepend that to my list here, and then return that. That should be the list containing the first n primes. And at that point, I have all my ingredients for recursion, and everything works great. So that depends on find prime being correct. To find prime, this is going to find a prime greater than or equal to the first input. That's where I'm starting my search. And it's going to take a list of all of the currently known primes. So every prime that I know about, the next value that I'm looking at, and then make a recursive call, or call this method, which is going to recursively call itself. Here I wanted to give you an example, a more complex example. You know, when I talk about fold left and fold right, I'm like summing up values and stuff. I want to show you a little more complex behavior, because especially if you tackle AO1, you might want to use these in more complex ways. So I'm going to take known primes, which in this case is a reference at 1, which is just the list containing 2. And I'm going to fold left, initialize at false. So start at the beginning of the list and visit each element with the accumulator initialized at false. So initially this will be the accumulator, the first underscore that appears. That'll be false. And then the value that I'm looking at here. I'm going to check if this is going to be my candidate prime. I'm going to check, is this the next prime? Right now it's 3. And I'm going to say false or 3 modulo my known primes, starting at the left, which is just the list containing 2. So 3 modulo 2, is that equal to 0? That's going to be false. So I have false or false. I've reached the end of my list, so this all returns false. I'm going to negate that to be true. And once that's true, I'm going to say this is the next prime. In short, in English, this is saying, is I divisible by any of the known primes? If it's not divisible by any of the known primes, it itself must be prime. So since 3 isn't divisible by 2, we're going to say 3 is the next prime. If it were not, we're going to make a recursive call and check the next integer. We're just going to check every single integer, incrementing by 1 each time, until one of them is prime. So the very first one we checked was prime, so we're going to return 3, and now we're going to see our list magic. So now we're taking 3 and prepending it to our list containing only the value 2. When we do this, we do not modify the list. Prepending, appending, anything does not modify the list. So at 1 is always going to be the list containing just 2. When we prepend, we create a brand new list containing the original list and any changes we made to it. So this list creates a brand new list starting with this one, prepend 3 to it, and then that's what we're returning, a reference to the new list that was created from this prepend operation. So we're returning a reference at 2 back up the recursion. And now this list will never change. This list will never change either. So any part of our program that has a reference to either of these lists will never be interfered with. We're never going to be able to change that data and mess up some other code that we're not currently working with. So now we're going to return that at 2. Max prime is going to be 3. We're going to make our recursive calls here. Now we get to our first candidate prime of 4. 4 is divisible by 2, so we're going to get our recursive call here. We're going to put another call to find prime on the stack, where we're going to check 5. 5 is not divisible by 2 or 3, so we're going to return 5. And here we have our same 4 ingredients. Everything's looking good here. If things are a little more complex here, if this is a prime number based on all our known primes, return it, else make a recursive call that gets closer to a base case where our base case here is finding a prime. So we're going to keep incrementing. We know that there are infinite number of primes, so if we keep incrementing and checking, we'll eventually hit a prime. So a little bit different structure here, but we do have our 4 ingredients there. We're going to return 5 and talk about the list stuff. This is going to prepend 5 to that list, which creates a brand new list. We have 3 lists on the stack now. Previous 2 lists unchanged. Every list will always be unchanged. We can't change a list ever in Scala using immutable lists, which is the default. So we have this new list with 5 prepended to it, and then we're going to return that back to our main method. The main method gets this reference at 3, which is the list 532, and that's what we're going to end up printing to the screen. So any questions on any of this? We got 2 examples of recursion on screen, and we're talking about list immutability. The big thing with list immutability is the same thing with strings. You have to reassign. If you changed a list at all, you're not actually changing it. You're creating a new list, and you're going to assign that to something. Here we're using that as the return value, and then assigning it right here. We have to do something with that. Any questions about this? All right, see you Friday.